Well, here we are with Newton's laws conceptual framework under our belt, right? You've got your horse-cart conundrum solved. You've got your reference frames figured out, right? Your inertial reference frames. You've got your action-reaction pairs. Okay, we're ready to take all of that and apply it to some problem solving. Problem solving in Newton's laws primarily involves Newton's second law, F equals ma. You'd be surprised how vexing those three letters can be, but also how powerful. I'm going to introduce to you a framework today that should serve you well in all kinds of Newton's laws problem solving, from the very simple ones, like the one we're going to do today, to very complex ones. Here we go. I think teaching a strategy works best with a concrete example, so let's take a look at the one on the screen. Okay, you have a block, okay, labeled B, mass 20 kilograms in the middle, and then you have the famous floating hands competing with one another, right? On the right, we have little floating hand, L, okay? On the left, big floating hand, B, but don't be deceived. It is the smaller hand that pulls harder with a force of 110 newtons, okay? And both hands are pulling on ropes attached to the block. Our goal is to solve for the acceleration of this block, okay? And hopefully the sign of acceleration will also give us the direction. Okay, I'm going to use an approach that I teach my first year students that I've abbreviated with the acronym SCLEPS, S-C-L-E-P-S, okay? S stands for sketch. So if the problem's in words, okay, it's not that case here, but in this case I've already done the sketch, right? But typically you'll have a problem in a book or on a test that's in words and you want to sketch it. After you've sketched it, you need to do the free body diagram, okay? The free body diagram is the foundation. It is where all the physics happens in a problem solving. So I've already done the free body diagram, so I'm going to switch screens now. Okay, go underneath. All right, here's the free body diagram, and that constitutes the end of the first step, right? Sketch. So you do the sketch, and if there's a free body diagram that applies, you do the free body diagram. All right. The next step, C, is to set up a coordinate system. All right. Coordinate system simply means where's the origin and which way is positive. I indicate which ways are positive by drawing a little coordinate system here, right? The direction of the arrow is the positive direction for that dimension, okay, up and to the right. And then also, if my object's moving, right, I would set an origin, like right here, for example, I write 0. We're not doing any displacement or velocity in this case, so the origin doesn't really matter. But that's part of the coordinate, setting up your coordinate system. Okay, the next thing you need to do is still part of the coordinate system step, which is this. You need to look at your free body diagram, and you need to compare the direction of each of those forces to your coordinate system. Any force that does not line up with one of the two coordinate axes, okay, means you're going to have to componentize it. It means you're going to have to break that diagonal force into its horizontal and vertical components. Okay, in this case, you can see that we have two forces. Okay, this one here and this one here that does not line up with the coordinate axis. So I'm going to have to componentize those. All right, and I've done that already on the next screen. Okay, so let's take a look at that. Right here on the right side of the screen, you see I've blown up the free body diagram larger so you can see the components. I've used SOHCAHTOA to find the X and Y components. I want to make a note for the AP test. Okay, when you do free body diagrams on the AP test, you often will be asked to do a free body diagram 4 points. Okay, it's important that that free body diagram be unsullied by any components. Okay, so in other words, this particular free body diagram here, right, you might get counted off because the dotted lines, the grader might mark as extra forces when really they're just components of a particular force, right? So make sure that your official free body diagram doesn't have any, like, in other words, over here you don't want to have anything like that, right? You want it to be clean, okay? No components on there. If you're going to sketch in components like I have, you want to do actually a separate free body diagram like I have on the right. Okay? So once you have your components, you now have all forces lined up in either the X or the Y direction. And now comes the crucial step of reading your, quote-unquote, reading your free body diagram into F equals ma. Okay? So now we're sort of transitioning in the SCLEPS approach to list, right? You might want to list your variables. We've kind of done that already on the drawing, right? F equals 50, M equals 20, things like that. That's the L step of SCLEPS. And now we've moved to the equation and the plug-in part. So let's take a look on the next screen here. All right, you see I've broken my work into x and y. Okay, I still want to keep track of that. Unfortunately, we're one-dimensional folks. One-dimensional folks when it comes to problem solving. Got to work in one dimension at a time. And I want to make sure that I'm clear about working in x, y direction. I write f equals ma in each direction. Okay, now here comes the crucial step. What I'm going to do is I'm going to take the left side of the equation, right, the sum of forces part, and I'm going to replace it with all the forces that I have for my free body diagram in that direction. In other words, I'm going to take this part here, okay, and I'm going to look up on my diagram. I'm going to say, how many forces do I have in the x direction? Well, I know they're hard to read on this particular diagram. I shrunk ours from the previous page down. But you see I've got this one here, right, and I got this one here. And I'm going to write them in symbol form. And I'm only replacing the left side of the equation now, right? The right side is going to stay ma. Okay, so that's going to be as follows. Let's see. I'm going to write the positive force first, okay? So that's force tension, right, from the little hand, okay, minus force tension from the big hand, like so, okay? And that's it. Those are the only two horizontal forces. And then I write equals ma. Okay? I'm going to do the same thing for the y side. I think you'll see that there are more forces there. I've got the normal force from the table. And then I have the two vertical forces from the ropes. Right? I've got force tension from big hand, force tension from little hand. And then the other vertical force, that's 1, 2, 3, of course, is the weight, right? But it's acting in the opposite direction. Now watch what I do on the right side here. It's ma again, but I know something about the acceleration in the y direction. It's 0, right? So I can substitute that in. All right, I'm going to pause again. I'm going to write in, I'm plugging the numbers, and then we'll take a look at what that looks like. Here you see it's the substituted values. If you look on the left side, you'll see that there's only one unknown in that equation. That's acceleration, right? I'll be able to solve this for acceleration, okay? And the right side is really just a gee whiz, nice to have for this problem. Okay, notice that the only unknown on the right side is force normal. So you'll be able to solve for force normal here. They didn't ask us to do that, right? But you'll find that the force normal, just like we said earlier, was less than the weight of the object. Actually, I didn't say that earlier. I'm going to revisit that in a minute. So let me pause. Here you see on the screen the final answers. Notice that we knew that the weight of the object, right, is mg, okay, and that's where this came from, okay. This actually comes out to 196 newtons, okay. So notice that the normal force in this case is less than the weight. And I don't know if you noticed that. Maybe you're surprised by the free body diagram. Let's go back to the free body diagram. Maybe you're surprised by what you saw there. Notice that it appears to be unbalanced, right? Notice that this force here, okay, is smaller than the weight, right? So at first it looks unbalanced. If you look at it, it looks like the box would be accelerating downward. But hopefully you'll see that the two ropes are pulling upward, right? So in fact, it's this component here, right, plus this component here, plus the normal force. Those all three together balance out the weight. That's why the normal force in this case ends up being less than the weight. And that's why you appear to have a free body diagram that at first looks vertically unbalanced, but to the trained eye, you start to see those balances that are in there. All right, this approach to problem solving, although we did a fairly simple problem, I think you'll find this to be helpful in even the most complex problems that you come across. Good luck.